Welcome to this lecture of the course Elements of Mechanical Vibration. In the previous lecture, we discussed the two major damping models, which included viscous damping and hysteretic damping or structural damping. Today, we are going to discuss in detail Coulomb damping, the dry friction damping, which also is prevalent in many mechanical systems. Okay, so the third common damping model that is in practice is the dry friction damping, also called Coulomb damping. It so happens that whenever the body has a relative motion, at the interface there is dry friction, which is going to generate a dissipating force, which is the frictional force, and that frictional force is the damping force that we have. Because of the fact that it generates heat, the energy available for the vibratory system gets dissipated, gets converted into heat, part of it. So, after each cycle of oscillation, through that dissipation, the energy available for the next cycle keeps reducing, and therefore, the amplitude of the next cycle is reduced, and we shall see how the vibration amplitude reduces in the case of a Coulomb damping. So, after the viscous damping and hysteretic or structural damping, the third damping that we are going to discuss is the Coulomb damping. The damping force is at the interface. Okay. There is no explicit dashpot here, but if this spring mass system, the mass is resting on a stationary surface, as you see here, and then when the mass oscillates and travels back and forth, the friction between the moving mass and the stationary surface generates a force at the interface, which is obviously we all know is given by mu into n, or in this particular case the weight of the mass is acting on the stationary surface, and therefore, n is actually equal to m into g. So, this friction force is going to act and is going to generate an additional force on the mass apart from the restoring force of the spring. So, if I consider a free body diagram of this mass, then at any position once it is disturbed, there will be of course the restoring force k, which is dependent on the displacement of the mass from the mean equilibrium position, but there will also be there will be a friction force mu n acting on the mass. Now, we all know that this friction force is going to generate heat at the interface, and that heat as it dissipates also absorbs or dissipates the existing vibrational energy, and therefore, as the mass oscillates about its mean equilibrium position, in every cycle some amount of energy is dissipated through friction and heat due to the friction, and that is how the amplitude keeps on reducing over subsequent cycles, and that is the kind of damping we have here. Because even in case of a viscous damping or a structural damping, it is ultimately the dissipation of the energy that reduces the total energy of the vibratory system, and that is the reason why all the subsequent amplitudes keep reducing, because in the next cycle not entire amount of energy that was available at the beginning of the cycle is available at the end of the cycle, and therefore, that is precisely the reason why the amplitudes keep dropping. So, the energy available here would not be the same as at the end of this particular cycle, and so this much amount of reduction in the amplitude is actually related to the energy loss due to these dissipating mechanisms. The dissipating mechanism can be viscous friction damping if there is a fluid separating the oscillating body and the stationary surface, or it could be even in the springs, even in the coil spring, the intermolecular friction creates heat, because the spring, if you keep on stretching and compressing, the heat is going to get generated because of the internal structural damping. So, in all of these cases, what happens is that every cycle of oscillation dissipates some amount of energy, and therefore, lesser and lesser energy is available at the beginning of the next subsequent cycle, and therefore, you have less and less amplitudes generated in the subsequent vibratory response. That is the whole the idea behind the damping mechanisms. Now, in this case, we had already discussed what is the character of the force versus displacement in a viscous damping case, and we saw that in the case of viscous damping, the force versus displacement graph for a cyclic motion is given by this elliptical one. In case of structural damping, because the structural damping is typically mass and spring together, the force displacement relationship typically is this. What kind of force displacement relationship we expect if we have a Coulomb damping in action. Okay. Now, this first statement itself tells us what kind of a relationship or what kind of a graph that we expect in a Coulomb damping. The damping force, which in this particular case is mu n, is obviously constant, because that force does not depend whether the mass is displaced by this distance or by this much amount of displacement, right. So, the friction force is always constant, opposes the motion, and that creates a constant dissipating force in action, right. And therefore, let us look at how this graph will turn out for a Coulomb damping case. Now, just assume that this mass has been pulled out through a distance equal to capital X, okay, and then released. Okay. So, when it gets released, the travel of this mass from this rightmost extreme to the leftmost extreme would have the friction force opposing that motion, right. Okay, so let's take this motion from the extreme rightmost point to the extreme leftmost point, and as the mass slides from the right side to the left side, the friction force we all know that is going to oppose the motion, and therefore, mu n is going to act in this direction. So, the position at the rightmost extreme, if it is shown here by this position x, and the mu n force is given on the force axis as equal to mu n, then the force being constant, it will trace out this path, and maybe if this motion is oscillating with a constant amplitude x, on the other extreme we can expect this to be the position of the mass at the other extreme. Now, when it reaches the leftmost extreme point, then it will start its journey back at its original equilibrium position, and in that case the friction force is going to oppose that motion, right. So, the friction force is now going to oppose this motion, and because it will oppose the motion, the friction force is going to be in the opposite direction to the motion. It is going to be suddenly changing to minus mu n. So, from plus mu n, the friction force will become minus mu n now, and so at the leftmost extreme it suddenly flips its direction, and for the rightward travel of the mass it remains constant, and when it reaches to the rightmost extreme point here, again it will flip its direction and then becomes like this. Okay. So, this gives us now the energy dissipated in a cycle for a Coulomb damping case. Okay. So, this square would obviously will have the energy dissipated in a cycle given by 4 mu W into x. So, W x obviously you can see that this mu n is nothing but mu times W or mu times mg, and that gives us the area within this rectangle to be 4 mu W x. Now, there is something which is added here, and that addition of the signum function here in the expression for the FD is only to take care of the sign as the whole oscillation happens. For example, in one half of the oscillation, let us say going from this end to this end, the direction is 1, and from here to here the direction changes and flips to from negative to positive, and that is what the signum function is included here to write the expression for FD. When we wrote the expression for the viscous damping case, then it was simply Cx dot. So, the direction will be taken care of by the instantaneous direction of x dot, right. So, that is included, but here the dissipating force is written mu W sin x dot. Now, why x dot, we will discuss that little later. So, hang on for a while, we are going to discuss why this signum function has x dot and not x. Anyways, so this is the expression of the cyclic energy dissipated in a cycle for a Coulomb damping. How does this help us in getting an expression for the damping energy dissipated in a cycle? We discussed that in case of the structural damping as well, or when we discussed the viscous damping case, that the cyclic energy dissipated helps us in comparing the energy dissipated to an ideal viscous damping case. Now, we have seen that in case of an ideal viscous damping case, the energy dissipated in a viscous damping case was pi c omega x square, and we equate this ideal viscous damping energy dissipated with the energy dissipated in other cases, right, in the other kinds of damping models. And then we say that this gives us an equivalent viscous damping coefficient from the other model. Okay. So, in this case this is simply going to be pi omega x square, and which basically gives me the expression 4 mu W upon pi into x. So, this expression is an equivalent viscous damping coefficient. Now, the practical significance is that here of course, we have a theoretical expression for a Coulomb damping case, but suppose we have a complex mechanical system and somehow we put that in a cyclic motion and extract the force displacement relationship or the graph relating the force and the corresponding vibratory motion, and somehow get the area under that force versus deflection diagram. This diagram is a measured one. So, it does not matter whether the dissipating force is contributed by viscous damping or of Coulomb damping or a structural damping. Once we get this area under this graph, which actually means that we are getting WD, and then we simply equate it with the equivalent or the expression for the Coulomb damping case, which is expression for the viscous damping case, and we equate that area, and then from that we get the equivalent viscous damping coefficient. And then because the mathematical expressions are well defined for a viscous damping case, we can simply use this value of the equivalent damping coefficient in the expressions to find out the response and other parameters of the vibration. Okay. So, that is basic philosophy of comparing or equating the energy in a cycle with different damping models. Many times the damping can be a complex damping, it could be contributed by different damping mechanisms at different components of a vibratory system. For example, here itself if you really look at this, there could be the dry friction damping at the interface, but there could be structural damping in this case. So, if you practically measure this, the whole all kinds of damping models or mechanisms will contribute to the dissipation, and then if you equate it with this particular expression, then we get an equivalent damping coefficient, and you can use that in the standard theoretical expressions of the system with viscous damping case to get the response, mathematical value of the response easily. Well, with this brief introduction to Coulomb damping, let us in detail find out how the response progresses for a typical dry friction damping case when we perturb it from a given equilibrium condition. Now, for that purpose we have assumed a simple spring mass system the way it is shown here, and what we are going to look at is how the motion take place when the body is released, let us say from this point. Okay. So, what happens is that there is an initial deflection displacement given to the mass, and the mass is released from this particular position. Displacement is considered positive rightwards. So, obviously, as the mass is pulled to its extreme displaced position, which we will say is going to be capital X here, and then as it gets released, the spring force which is coming into action because of the stretched condition of the spring as the displacement is given, it tries to pull the mass towards its mean equilibrium position, but in the bargain it because of its own inertia, it does not only come and stop here at the equilibrium position, it continues to slide on the leftmost extreme position because of the inertia, and so the spring gets compressed as it goes past the mean equilibrium position, and it would settle down somewhere here in its leftmost extreme position. And after that, once an equilibrium is reached there, once the velocity comes to 0, kinetic energy will be 0, the strain energy in the spring will reach its maximum value, and the compressed spring will now try to push it back again to its equilibrium position. This is how just like our pendulum case, the body keeps on swinging around the mean equilibrium position. So, x equal to 0 at this point, and we are looking at the motions starting from t is equal to 0 at this rightmost extreme position. So, if I plot this motion, let me plot it here, and so the initial position is capital X, positive displacement given, and then I am releasing it, right. So, in this particular position, the free body diagram of this mass, if I can show here, the spring force is going to act in this direction. Okay. So, during its travel from this point on the backs on this side, kx is going to act rightwards, but because the motion is happening towards the left side, at the interface the friction force will act opposite to the direction of motion. So, the friction force on the body is going to be mu times the normal reaction. Now, the body has a mass m. So, if we look at the force which is going to act on the body is mg, and there will be normal reaction. In absence of any other force in the vertical direction, they will balance each other out. And so, this friction force will act in this direction. Okay. So, now if we apply the Newton's second law for this motion from this the rightmost extreme point to the leftmost extreme point in the first cycle, sigma f is mass times the acceleration, and the acceleration is assumed positive in the rightward direction. So, we have mx double dot equal to minus kx plus mu n, right, and therefore, the equation of motion that governs the motion of the mass is going to be this. Now, what will be the solution of this equation of motion? So, you may notice that this friction force is independent of the displacement, right, and it has rightly been on the right side of the equation on the equal sign. So, this can be treated like a constant force, acting on this mass. Now, just like the gravity force that was acting on the mass and it generated a static deflection, similarly the response because of this constant force on the right hand side will also generate similar kind of a steady deflection, right. That deflection is going to be a constant value, and what will that be? Correlate, compare it with respect to what we discussed for a vertical spring mass system. The gravity created a deflection, static deflection, which was mg over k, right. So, if this body when it is hung from the spring, if it was subjected to the gravity load, the deflection delta that we wrote last time was mg the force over k. That is what the spring rate is. Mg over delta is the spring rate. So, if k is the spring rate of this of the spring, then a constant force like mg created a static deflection delta. On similar lines, the response because of the constant force mu n is going to be generating a deflection which is going to be mu n by k, is it not, right. But in addition to this right side force, we notice that the left hand side equation of motion, which has the left hand side mx double dot plus kx equal to 0, that would generate its own free vibration response, is not it. So, the total response for a linear system is going to be addition of the two responses, and you remember that for a vibration, the governing equation of motion for a simple single degree of freedom system, free vibration response was what, x of t equal to a cos omega n t, and then the cosine and sine, both terms were there, right. So, a and b we found out from the initial condition. So, this is the general solution of an equation of motion like this, right. So, in addition to the response generated because of mu n constant force, there will be this response coming from the left hand side part. Okay. So, the net response in this case would be a general solution of the governing equation of motion that we wrote here, is going to be A cos omega n t plus B sin omega n t plus or minus. It would be plus because it generates the response in the direction of the force. The force is acting rightwards, which is x positive. So, it is going to be plus mu n by k. That is going to be the response of the system, which is defined by the governing equation of motion when the mass moves from this extreme right side position towards the left side position. Isn't it? Okay. So, let us now check to what extent it will go to the left side, and for this half cycle of motion, half cycle in the sense that what we have discussed is that it starts from the extreme right side position and then it goes to the left side position. Left side position is in the minus x, I mean negative direction of x, okay. X is positive rightwards. So, this is x equal to 0, it will go on the left side, that is negative x. Where would it stop? Now, obviously, there is no damping as such involved, which is the viscous damping term C x dot here. So, in the kind of equation that we have here, the homogeneous part m x double dot plus k x equal to 0 will obviously generate the response which is harmonic with the undamped free vibration natural frequency. Okay. So, that is the reason why this frequency that we have used here in this solution is the natural frequency, undamped natural frequency of vibration. So, the oscillations are going to happen at undamped natural frequency of the system, because what we have done is we have got a solution which is a linear mixture of the solution of the homogeneous part and the response because of the constant force mu n appearing on the right hand side, right. So, we simply superpose the two responses. Mu n by k obviously is a constant value, and this part is going to generate oscillations in the vibratory system. A and B are some assumed constants. We do not know what the values of these A and B will be, and therefore, if we want to trace out this path of the vibratory motion of the mass, we will have to find out the expressions for A and B. How would you find A and B? We have done that part earlier, right? A and B are unknown constants, right, in the assumed solution, and those expressions for A and B are always obtained from initial conditions, right. So, for initial conditions, meaning at t is equal to 0, what are the initial velocities imparted to the mass and what is the initial displacement. Now, let us first get the expression x dot t, so that we will be able to apply initial conditions. So, this is going to be what? Minus a omega sin omega n t plus b omega n cos omega n t, isn't it? This is a constant term. So, the derivative is 0. So, that basically these are the two displacement and velocity expressions we have. Okay. What are the initial conditions? What have we done? We have released the mass from this extreme rightmost point and we simply released it, right, meaning thereby that the initial velocity is 0, right. So, at t is equal to 0, x at t is equal to 0 is x naught, which in a general terminology we write this as x naught, which I can write as capital X, because that is the amplitude with which I have released the mass initially. And obviously, x dot at t is equal to 0, which we typically write as v naught, is 0 in this case, because we have simply stretched it to capital X and just released it to slide, okay, oscillate. So, initial velocity was not imparted. So, v naught is 0, which actually means from these two expressions capital X would be equated to what? A plus mu n by k. The sign term will be 0. So, obviously, A is going to be capital X minus mu n by k. And if I use the second equation here, so this is based on the first equation. If I use this equation, 0 is equal to B into omega n, which actually means that B is 0. So, the final solution, right, the final solution I have for this motion of the mass is, sorry, it should be x here, capital X minus mu n over k cos omega n t, B is 0 plus mu n over k. Is it not? Okay. Now, you should note here that this is the solution of the governing equation of motion when the mass moves from right to left. Please make a note here that this direction of the friction force has been taken considering that the motion happens from right to the left, right. In a typical oscillation of a vibratory system, this is just half the cycle, right. Going from right extreme to left extreme is just half the cycle, it will come back. But when it comes back, its direction of motion changes, the friction force will flip its direction. So, it means that this the response x of t is not going to be valid for the reverse travel or the second half of the cycle. So, we will have to now look at what equations of motion should we be getting for getting the second half of the first cycle. So, obviously, as you notice that when it tries to go from this to this, the kx, the stiffness related restoring force is going to act in the rightward direction, and the friction force is going to flip its direction. So, it is going to be this equation of motion mx double dot plus kx equal to mu n is going to change to mx double dot plus kx equal to minus mu n. The direction of the friction force is going to change, right. So, I am going to update the equation of motion for the second half cycle of motion. The governing equation of motion is going to be, as the motion happens from left to right, the friction force in that case is going to act in the leftward direction. And if we now want to write the equation or the solution of x while it gets from the left to the right side, what is the solution? The general solution is still going to be given by this, except that there will be small change here. So, what would that be? So, x of t, okay, of this governing equation is going to be equal to what? Again, what we do is we assume some constants. Now, in this case I will use two different constants, cos omega n t plus d sin omega n t. Make a note here that this part is still going to generate response at the undamped natural frequency of the system. So, this solution, a general solutions is valid for this case as well. However, the response due to the constant force on the right hand side is going to be similar, except that the sign in this case is going to be changed. So, this is going to be mu n over k, but in this case it is going to be minus mu n by k. So, now if I want to write the velocity expression, then it is going to be minus c omega n sin omega n t and plus d omega n cos omega n t. These are the two displacement and velocity expressions for the motion of the mass when it is going from this left extreme position to the right extreme position. During that travel, these two equations are valid. Okay. Now, how do I find C and D again? Initial conditions. So, what will be initial conditions? So, now because this equation is different, this equation is different and this equation is different. So, what we say is that the motion from here to here is governed by a different equation of motion. So, therefore, when I want to now know the response in the second half of the cycle. So, this is the first half of the cycle, first half cycle, and in the second half of the cycle some other equation applies. So, when I started getting the equation or the response of this half cycle, I use initial conditions at this point, right, at the beginning of that cycle. What we are going to do now is assume a fresh time. Okay. Now, we are going to treat this second half of the cycle as a fresh cycle, which is going to be generated through this governing equation of motion. So, we are going to start looking at the response by assuming initial conditions as it exists at the end of the first half cycle. Okay. That becomes the initial condition for the second half cycle. So, at the end of first half cycle, what is going to be our initial displacement and initial velocities? That is what we are going to obtain. So, we shall try to get those constants C and D by substituting appropriate initial condition. Now, when you want to substitute the appropriate initial conditions, I would like to know what is x at time t equal to 0, time starting from this point onwards. Please make a note that time actually starts from here, but we are now shifting our initial position of our initial time to be at that location, just for the sake of getting an expression. Now, if that is the case, the displacement or the response in terms of displacement and velocities both at this location should be known, and what is this location for this half cycle? That is going to be what? It is going to be, see, this period is for one full cycle. So, for half cycle this is going to be, instead of 2 pi by omega n, it is going to be pi over omega n. For half cycle it is going to be pi over omega n and not 2 pi over omega n, because the oscillations are still with omega n. So, let me write this x at t equal to pi over omega n is equal to capital X minus mu n over k. This cos term is going to be cos omega n. What is t? T is pi over omega n, isn't it? And plus mu n over k. You get it? So, mu n over k and this omega n. So, what is cos pi? Minus 1. So, this is going to be minus of capital X minus minus plus mu n over k and plus mu n over k. So, that basically is minus x plus 2. Now, we are going to make use of this mu n over k many number of times. So, what I will do is I am going to represent mu n over k by this delta sign. So, that it becomes convenient for me to keep writing those terms. So, assuming that delta represents mu n over k, minus x plus 2 delta is my response x naught now for these two equations. That x naught I have got by using the the response of the first half cycle at t is equal to pi over omega n. So, this response is, or this amplitude here is minus x plus 2 delta. What does it mean? What does it mean now? I have a positive x as the amplitude to start with in the first beginning of the first half cycle, and as it goes on the other side, as it goes on the other side, it does not go right up to minus x, right. You remember in an undamped free vibration, the amplitudes do not change, right, on both sides the amplitude remains. So, if it starts from plus x, it will go to minus x, it will go back to plus x and then minus x and so on. This is undamped free vibration. But what we are observing here is that at the end of the first half cycle, the amplitude drops by plus 2 delta. I mean drops by 2 delta. So, this actually is the amplitude which is not minus x, but minus x plus 2 delta. The amplitude is reduced by a value 2 delta. What about V naught? What is the initial condition V naught for the second half cycle? It will be 0, you can check that yourself. Take the derivative of this expression which is x t, because this pertains to the motion in the first half cycle. What will happen when you take the derivative, the constant term vanishes and this term becomes sine, and then sine at t is equal to 0 or t is equal to pi by omega n will turn out to be 0. So, ultimately there is no velocity at the end of the first half cycle, and therefore, our initial conditions for these two equations, okay, these two equations which we wrote for the second half cycle, we will have to now use x naught and v naught which we have obtained from the previous half cycle's response, will have to be used into these two equations to get the expressions for C and D. Okay. Now, with these two equations defining the motion in the second half cycle, x of t at t is equal to 0, where t is now defined from this point for the second half cycle. So, now we have reset our initial time at the beginning of the second half cycle. Now, if that is the case, then what is the expression at x at t is equal to 0? You can substitute for t is equal to 0 in this equation, which gives us C minus mu n over k. Now, again this mu n over k, I am now going to use delta as I discussed, C minus delta, because when t is equal to 0, this term is 0. So, C minus delta, where mu n over k is denoted by delta, just for the sake of convenience. I can keep using mu n over k, but just for convenience sake I am substituting mu n by k by delta. And what about x dot at t is equal to 0? That is going to be so d into omega n, that is the equation that I have by substituting t is equal to 0. Now, x at t is equal to 0, we have already obtained that value from this expression, I mean by substituting t is equal to pi over omega n from the first half cycle's response, and then this value x at t is equal to 0 is the initial condition which I have already found, that it is equal to minus x plus 2 delta. Okay. And this value being 0, it also tells me that d is equal to 0, and from this expression, okay, I have a value of C, equal to minus x plus 3 delta. Okay. Now, I have d equal to 0 obtained from substitution of initial conditions, and I have expression for C obtained likewise, and then therefore, these two equations which define the second half cycle can be completely written, everything known in that case. So, now I will write x of t, the response in the second half cycle, to be equal to C, which is minus x plus 3 delta, okay, cos omega n t, and d being 0, it simply is minus delta, because I am writing mu n by k as delta. So, with this I have the response obtained for the second half cycle. So, this is the response that governs the vibratory motion of in the second half of the total oscillation. What we should be making a note of is, if we compare this with the response that we obtained. So, this is for the second half cycle. What was the response that we obtained for the first half cycle? This was x minus delta cos omega n t minus delta, plus delta, I think, yeah. So, this was for the first half cycle. Now, just focus on the expression for the first half cycle. Please make a note, it shows that there is a constant bias value in the response which is mu n over k, that is delta, which means that this motion, the first half cycle motion, is going to have a mean position around which the oscillations happen given by delta. So, this displacement is delta value, okay. And the amplitude with which the harmonic oscillation happens. So, this is going to form a cosine waveform cos omega n t, which means that this motion is going to follow a cosine function, which is obvious from this expression that we have, with an amplitude x minus delta. So, obviously, this amplitude with which the cosine function is shown here is x minus delta, which is obvious, because if this is delta and this is the initial displacement we released it with capital X. So, this x minus delta is the cosine waveform with which it is going to oscillate, and obviously it is no surprise here that at the end of the first half cycle that amplitude gets reduced by 2 delta value, is not it, because if it has a mean value here offset by delta, the amplitude at the end of the first half cycle would obviously be x minus 2 delta. And what happens in the second half cycle, that the oscillation continues now. So, let me draw it properly. So, in the second half cycle, what is the expression we have is minus x plus 3 delta is the amplitude, which means that the amplitude with which this cosine function operates obviously has initial value, or it is minus x plus 3 delta. So, at t is equal to 0, what will this value be? Minus x plus 2 delta, right, and the oscillations will happen with a mean which is shifted by delta value. You may notice that it is already started with minus x plus 2 delta, and the mean is shifted with additional delta. So, this mean is shifted here with an additional delta value with which this cosine function will oscillate, cosine function will behave, and there is a bias of minus delta, which is of course on the negative direction here. So, just have a look at what will happen at t is equal to pi over omega n, which is the end of the second half cycle. Now, which means that this is going to be x of t at t is equal to pi over omega n. What will this be? Minus, and minus will become plus, because minus of minus x plus 3 delta is going to be plus x minus 3 delta and minus delta. So, which means that at the end of the second half cycle, the amplitude in the second half with respect to the original amplitude of x gets reduced by a value equal to 4 delta. So, this is 4 delta value with which the amplitude gets reduced, and that is what we have observed here. Is that correct? So, x minus delta is with which with this amplitude the first half cycle exhibits response around that mean position with that amplitude. In the second half, this amplitude because the response is around a mean position which is shifted negatively with respect to this 0 position. So, about this mean equilibrium position the oscillations take place obviously because this is already an amplitude which is reduced to minus x plus 2 delta, or minus I can write this as minus of x minus 2 delta, and then you add additional delta which is shifted here, this obviously becomes x minus 3 delta. Okay. So, that is how the second half cycle oscillates with a cosine function with an amplitude of x minus 3 delta. This again is a cosine function, and at the end of the second half cycle, the amplitude that actually gets reduced with respect to the original amplitude before the first cycle started is 4 delta. Okay. Now, you can continue with the next full cycle, and it is obvious that the next cycle of complete oscillation will again reduce by the same value 4 delta, and where delta is mu n over k. So, do you see some important difference between the viscous damping and the Coulomb damping case? Amplitude decreases linearly, right. So, here in the first half cycle the amplitude drops by 2 delta, in the subsequent half cycle it drops by another 2 delta. Overall, if you consider the amplitude a unit amplitude at the beginning of a cycle, at the end of that cycle it will get reduced by 4 delta, and this continues, and therefore, which actually means that the amplitude drops in a Coulomb damping or a dry friction damping by a constant value, and which actually means that the envelope, if we draw an envelope touching the peak values of each of these cycle, it will be a straight line. Okay. So, there is a linear drop in the vibration amplitude in case of a Coulomb damping, which is in contrast to the viscous damping case where it reduces exponentially. So, these are the free body diagrams of simple spring mass system under dry friction damping or Coulomb damping, and we discussed that in one half cycle the free body diagram for the same system changes from one half cycle to the other half cycle. So, this equation of motion is valid for one half cycle, and this equation of motion is valid for the other half cycle, and the overall governing equation of motion, instead of writing them separately like this, we can write them jointly like this, and later on we will discuss how we can take care of this plus minus signs by using the signum function. Now, this is basically going to mean that our equation of motion is not a linear equation of motion. Why? Because they depend on the signs of this friction force at each instant of time, and therefore, the governing equations are not linear in case of a Coulomb damping case. Now, this takes a recap of what we have derived earlier of the reduction in the vibration amplitude after every half cycle of oscillation for a Coulomb damping, right. So, we started with some initial amplitude, let us say capital X at this point, and we knew that this equation was used, and then you got after one half cycle up to this point, which is of course pi by omega n value, the first half cycle vibratory response is about this mean point, which is shifted by a value of mu n by k. So, it is a cosine function about this particular amplitude or level, and on the other side the amplitude gets reduced to x minus 2 mu n by k. That means, the original amplitude x gets reduced by a value equal to 2 mu n by k, right. That is what we discussed, and then when we subsequently found the response to the next half cycle, the next half cycle was again a cosine function or a cosine term with this as the mean value. So, the mean value gets shifted from a mean equilibrium position 0 mean equilibrium position, the mean point gets shifted by a value equal to mu n by k again. And at the end of the first cycle, which is after 2 pi by omega n, the amplitude finally is left equal to original amplitude minus 4 mu n by k, right, which actually means that the drop in the amplitude is going to be 4 mu n by k for one full oscillation cycle. Okay. This is again important to note that this half cycle shown by the blue color is following an equation of motion which is a linear equation of motion, but for one full cycle it is no more linear, it is bilinear, because in this half cycle it follows one particular equation of motion, let us say mx double dot plus kx equal to plus mu n, and in the other half cycle the sign of that friction force changes and some other equation slightly different in terms of the sign of the friction force applies for the second half. But for one full cycle the governing equation is not the same the way we have in case of a viscous damping or a structural damping. And yes, after one cycle of oscillation the original amplitude drops by 4 mu n by k, and it is possible to show that in the next subsequent full cycle the amplitude will further drop by 4 mu n by k. So, the amplitude after 2 cycles will be x minus 8 mu n by k, right. So, with respect to original x, this is going to be a drop by 8 mu n by k, but the point is every cycle sees a reduction of a constant value in its amplitude, which actually means that there is a linear decay of the amplitude. In earlier case of viscous damping, what we noticed that the amplitudes x1 and x2 are in constant ratio, okay, and the ratio of the two subsequent amplitudes are constant in case of a viscous damping. Whereas in the Coulomb damping, there is no relation for the ratio, but in case of the Coulomb damping, as we notice here, x1 minus x2, the drop of in the original amplitude or the difference in the two consecutive amplitudes is constant. That is what the difference between these two dampings are. Okay. Another interesting thing here is going to be like if we see that this mass which is continuously in oscillation against the friction force, it so happens that after a while, after a certain number of cycles, we know that at any point of time the force by spring is going to tend to restore the mass to its original equilibrium position, but a friction force is going to constantly oppose that activity, right. So, kx and mu n they will differ, and that keeps the mass moving back and forth. And so, it so happens that later on after several number of cycles maybe the amplitude x will fall to such a low level that the restoring force kx will no more be able to counter the constant friction force, which is going to be a value which is constant irrespective of the amplitude of oscillation. So, the motion will suddenly stop when this kx and mu n will be almost equal, or what we can say is that the restoring force will fall short of the friction force. Okay. The friction force will be a constant value, and the restoring force is going to be will diminish as the amplitude keeps reducing every cycle by cycle. So, after some certain number of cycles, the restoring force k into xn will be less than the friction force, and then if that happens the motion will stop because the mass will not be able to move any further. And this is what is shown here. Probably after this after the second cycle, what can probably happen, that at the beginning of this cycle maybe the friction force was good enough, strong enough, but here it was strong enough, but by the time it reaches here, the restoring force k x n at the start of the third cycle will be less than mu n, and then at that point the mass simply gets static or locked, and then because it is locked, as time progresses the amplitude is going to be remaining static and constant equal to this value. Now, it is possible to get a relationship as to after how many half cycles this will happen, right. So, what we can say is that if R represents the number of half cycle, and we know that after each half cycle there is a reduction in the amplitude by 2 mu n by k. So, the number of half cycles R after which the motion will stop will obviously be given by this expression, that original amplitude will get reduced by R times 2 mu n by k, because every half cycle 2 mu n by k gets reduced. So, obviously after R number of half cycles, this is how this total number of the total reduction will turn out to be this. Now, if you want to compare it with this, you need to use this expression to get the value of or expression for R. So, you can reorganize this expression to get the expression for R. Okay. So, if you know what is your initial amplitude, then it is possible to find how many half cycles after which the motion will cease. And in fact, this is an important distinctive feature of a Coulomb damping that you should understand, that the mass will never come to a zero or original equilibrium position, and it so happens that it can suddenly get locked to a non-zero position or away from the equilibrium point. The viscous damping, in contrast, will come to its mean equilibrium position as time t progresses. It will eventually come to mean equilibrium position, but a Coulomb damping will not return, the system will not return to its mean equilibrium position, and that is one distinctive feature to identify from the practical measured data whether the damping is a Coulomb damping or a viscous damping. And finally, let us look at how we can combine the two equations of motion, the one which is in the first half cycle and the other one in the next half cycle, using function called signum function. Now, for that to happen, let us take another look at how the motion has been happening. So, when this mass is taken on the right side, and then from this extreme rightmost position, the mass starts its reverse journey in this direction to the leftmost extreme point. The motion we have discussed is shown like this half cycle. Okay. So, from this x position to a position here which was basically x minus 2 delta. Now, when this is happening, from our free body diagram of the mass, we know that the restoring force, because of the spring, was acting in this direction. The friction force was acting opposite to the motion. That is how it was shown. And now, for this first half cycle motion, the equation of motion has been obtained earlier as mx double dot plus kx equal to mu n. This is precisely what we derived earlier. In the second half cycle, when the mass is actually moving from the left extreme to the right extreme point, in that case, the free body diagram, if you really look at, the restoring force is still kx, and this motion is happening here. So the friction force is now flipped in the opposite direction, and this is how the mu n was shown. And for this particular second half cycle, the equation of motion now is mx double dot plus kx equal to minus mu n. Okay, so I may write this equation as mx double dot plus kx minus mu n equal to 0, and this second cycle equation as mx double dot plus kx plus mu n equal to 0. Somehow, if for an entire cycle, if you want to get one single equation, because in case of the Coulomb or hysteretic damping, the equation of motion was not split into two half cycles. Okay, so for that purpose, what I would like you to understand is this equation is essentially giving a harmonic cycle which is with cosine omega n t, the displacement of the mass that happens like this, right? If you want to write about the velocity, of course the exact expression is going to involve additional terms like what we have derived, that it has to be x minus delta or x minus 2 delta times cos omega n t. But in general, for a harmonic motion, we all know that the velocity term is going to look like this, minus x omega sin omega n t, which actually means that the velocity amplitude is going to be x omega, and it is going to be negative in the first half cycle. And so if I plot, velocity is going to be seen like this. Okay, when this crosses 0, your velocity value is going to be maximum, and of course this the value is going to be omega times the x if it is a harmonic motion. The most important aspect of this relationship between the displacement and velocity is that for the first half cycle, the sign of the velocity is negative. Okay, so and obviously what will happen is that as the motion continues in the second half cycle, if it continues in the second half cycle as we have seen, the velocity is going to be positive in the second half cycle. So this is going to be positive, and for the second half of the travel. So this fact I can include in writing now the governing equation of motion. So because there is a negative sign here, what I can write this equation as mx double dot plus kx. If I want to combine both of them, I can write this as minus plus mu n equal to 0. Now minus when it is in the first half cycle, okay, and plus if it is in the second half cycle. Now because I already have a clear idea that in the first half cycle the sign of the velocity is negative when the displacement changes from plus x to minus x. So therefore I can simply write here as plus signum function of what, now it should not be a displacement. Why? Because in the first half cycle the displacement flips from positive to negative sign, so it is not always positive in the first half cycle. Okay, but velocity is definitely continuously negative in the entire first half cycle, and therefore I can use sign of the velocity times mu n to represent the entire oscillation. Okay, so this is basically is the way I represent the governing equation of motion for Coulomb damping in a single equation, making use of the signum function, and that is the way in the initial discussion we saw that the dissipating force Fd was written as mu n sine of x dot. That was written essentially to account for the sign of the friction force. Okay, so this is the governing equation of motion for the entire cycle. In the previous discussions, what we did was just to understand how much is the drop in the initial amplitude in one cycle, we split the total motion in two half cycles. Each half cycle had this kind of a linear governing equation of motion. Okay, one independently for the first half, the second independently for the second half, and we combine now these two equations for the two half cycles into a single equation. But this signum function being a function of the velocity or the response variable, the signum function causes this equation of motion to be non-linear equation of motion. Okay, if you consider the equations of motion in two separate halves, then in each half cycle they are linear. So that kind of a non-linearity we call as a bilinear non-linearity, wherein it is linear in part of the total cycle. Here by bringing in the signum function, definitely the equation of motion for the Coulomb damping has turned out to be a non-linear governing equation of motion, in contrast to mx double dot plus cx dot plus kx equal to 0. This was a linear governing equation of motion for a viscous damping case. All right. With this, now let us have a brief discussion on the differences between viscous and Coulomb damping. Right? There are distinctive differences. Obviously, let's take them one by one. Distinction, of course, is based on frequency of oscillations. Now we know that in case of a Coulomb damping, the response x of t was obtained as x e to the power minus zeta omega n t cos omega dt minus phi. Now this actually means that the frequency is the damped natural frequency, whereas in the case of Coulomb damping, we have noticed that the response obviously does not have this exponentially reducing amplitude, but the cosine function involved was omega n t. So the frequency with which the system with Coulomb damping oscillates is the undamped natural frequency. Okay, based on the nature of governing equations, we discussed just now that the Coulomb damping has nonlinear governing equations in contrast to the linear governing equations for the viscous damping. Based on the decay of oscillation amplitude, we already discussed that the viscous damping exhibits exponential decay of the initial amplitude, whereas in case of a Coulomb damping there is a linear decay. In other words, the ratio of successive amplitudes is constant in case of a viscous damping, whereas the difference in the successive amplitudes is constant for a Coulomb damping case. Then we also discussed that in case of Coulomb damping, because of the friction force being constant, after a certain time, if the amplitude of vibration drops below a certain limit, the motion ceases and the system or the mass simply gets locked at a particular point, and therefore in Coulomb damping the mass does not approach mean equilibrium position, whereas in case of viscous damping the final amplitude will become 0 as time progresses. And of course the damping force in case of a viscous damping is proportional to velocity. It is velocity dependent dissipating force, whereas it is constant in case of a Coulomb damping. And essentially a Coulomb damping is periodic with the harmonic time function of the undamped natural frequency, whereas depending upon the value of the actual damping, viscous damping, the system can exhibit an aperiodic vibration response for the viscous damping case. Right? So these are all the distinctions between these two kinds of damping. Now, where are these Coulomb damping case actually seen in practice? So, there are many examples and many places where you would observe a friction damping or a Coulomb damping, and one of the peculiar application is in the steam turbine blades, sometimes also in some stages of the gas turbine blades. So, you can see these bladed discs at different stages. Long blades are basically in some stages. The tips of the blades are made in a very special shapes. So, these tips are made with different shapes. In addition to that, the blades are inserted in the discs at these dovetail grooves. You should notice that this disc is carrying many blades at its periphery. These blades are actually inserted in the slots. So, if you see, these are the blades. Okay, all these blades are inserted. This is your disc. In the disc we have these kind of slots which are called as the dovetail grooves. In these slots the blades are inserted. So, this is the disc and this is the blade root. These are inserted and you can see that they are not rigidly held, they have some gap. Okay. So, these gaps are responsible for some friction damping at the root, and as the blades vibrate with large amplitudes, there will be small interface displacement and some slip motion between the stationary component and the vibratory blade component at the root, and that generates some amount of damping which can help dissipate resonant vibration vibratory displacement of the blades. So, this is one place where the Coulomb damping is actually designed in. Okay. So, the friction between two bodies helps us generate some damping to reduce or contain or attenuate vibratory displacements. More than that, one of the main source of damping in such long blades is at the tip. So, we have seen at the roots how the Coulomb damping can be enforced, but these blades do also, some of the stages of course have these kind of shrouds. Okay. So, the tip of the blade has these kind of a Z shape projections, and so on the trailing side you will have this kind of a slot, and the previous blades leading side will have this kind of a projection. Okay. So, you can see that here, and as the blades vibrate, the lateral vibration of the blades also cause simultaneous torsional motion, right. So, the blade will also move this way and also move laterally, and the net motion is going to create friction because these projections are going to create a friction. As the blades vibrate, they will rub against each other, these tips are going to rub against each other, and that rubbing action is going to generate vibratory attenuation of vibratory displacement through dry friction damping. Okay. So, these are called as the Z lock arrangement, and these tips of the blades are designed to generate friction damping, and that is how substantial amount of vibration attenuation can be obtained. Okay. Based on this, now you can try and attempt these questions, and then of course, as we always do, the next slide will give you the answers to these questions, but try and attempt them yourself first before you see the answers. So, in this lecture, what we discussed was Coulomb damping, and how the Coulomb damping or dry friction damping is accounted for in the governing equation of motion. In particular, how the initial amplitude decays because of the presence of Coulomb damping. We understood that the equation of motion is nonlinear and the decay in the amplitude is linear. So, apart from viscous and structural damping, this third important damping was discussed in detail.